Right. So in the previous video, we talked about self-attention, but it was quite simple because we didn't include trainable weights. As you can see from the title of this video, we are now going to do self-attention, but add trainable weights. It's pretty much the same concept. We want to compute context vectors as weighted sums over the input vectors. What we are going to then, and it is with respect to a certain input element. So we can compute context vector for input element number two, taking into account all the other input elements. It's the same concept. What we're changing now is previously we just had those alphas without training them, but now we are going to introduce what are called weight matrices that will be trained during train that will be optimized during training. So we're introducing weight matrices. So these trainable weight matrices, they are very crucial so that the model can learn to produce good context vectors. The ones that we had previously that were not trained meant they were set in stone like that. But these ones, at least they get optimized during training, meaning they'll probably perform much better to produce better context um, context vectors in that attention module. So we'll do what we did previously. We'll focus on one input, do it step by step, and then we'll just do for everything. We'll do for every input to calculate all the weight matrices. So what we are going to do is I'm going to write a diagram that I'll probably be coming back to. That I'll be coming back to because we need to add step by step. So you might see me jumping up and down the this screen, but hopefully it will all make sense by the end of this video. So we are going to introduce these weight matrices, and they are going to be, we're calling them WQ, WK, and WV. This is the query matrix. These are the keys. So these are called the query. So this is the query matrix, this is the key matrix, and this is the value matrix. We'll see what those are. Just keep in mind that that's what we are working with. So the three matrices we are working with. They these are used to they are used to embed the input tokens. So xi into what is called the query, key, and vector and value vectors respectively. So when we have our inputs here and we apply when we have our input elements like we had previously, and we apply these matrices, when you apply the Q matrix, it embeds it into the query vector. Apply the K matrix it will embed it into the key vector. And when you apply the WV matrix, it will embed into the value vector. And we'll see how they do that. So let's focus again on the second input. So let's now write our process. So we have your was our x1, and it had 0.4, 0.1, and 0.8. Those are the only three dimensions we are considering right now. And then here we'll have journey, which we are focusing on. Journey, it's not actually capital letter J, it's just small letter j, because in large language models, capital letter J and small letter j, they sort of have meanings. So this one's 0.5, 0.8, and 0.6. Nice. And then it goes on like that all the way up to the last one, which is step. The last one is step, which is our xn. And our xn is just 0.0, 0.8, and 0.5. That's it. That's what it looks like, right? So now that we know how it looks like, what we are going to create, we are going to create those WQ, WV, WK, WV. So because we are focusing, our focus is on this one here. This is what will give us the query, because you remember it was just a query even previously when we had when we were not dealing with trainable weights. The input that we're discussing at that point to create the context vector for was called the query. So Jenny will have a query vector. It will have a query matrix, so query matrix WQ, and it will have its own WK and also a WV matrix. The ones that we are not considering at that particular step, we just have the W key, Q, okay, I'm saying W key, but yeah, it is the Q matrix, and then WV. Here we are just the matrix. I'll write the matrices now, and then here it would be WK, and then and then WV. So what we're doing is, how do we get these matrices? That is a question. So what we will do, we'll explain how the matrices are, how we get the matrices. You see them in code. I'm just going to write down the process, and then we will discuss them. So here our W key K is 0.3, 0.7, and WV is 0.1, 0.8, and then WQ is 0.4, 1.4. And then WK for this one is 0.4, 1.1. WV here 0.3, 1.0. And lastly, 0.3, the last batch here 0.9. And then 0.3, 0.7. Okay. Now at that stage, here we say this is the value vector, because here we're dealing with vectors. We're only dealing with one query at this stage, right? Like we did previously, we focused on the second one, and then we expanded it into doing it all in one step when we do the matrix multiplications and all of that. Here, this is coming out. The WV is coming out as a vector because we're just dealing with one. But when we expand it, it will be a WV matrix because we're now dealing with all inputs at the same time. But this value vector here is corresponding to the first input token obtained by matrix multiplication between the weight matrix WV and its input token. So we are going to have a weight matrix here where we are going to multiply this x1 by that value matrix here, and this is the result, which is a value vector. This is the value vector here. It's the same thing. We are going to have a matrix that is called WQ. To get this now, we are just going to say input x2 matrix multiplied by WQ, we get this result. That's the same thing. We have a WK here, we multiply the input, and we'll get this result. That's what we are having. So now you will ask, so this I'll just add some of the calculations here because I think it would be good to just put them there. So our query vector is just, so it's going to be, for that particular I that you're dealing with, is equal to W Q X I. So our query vector 2, our Q2, this is our Q2. Q2 is equal to WQ, which is a WQ, times X2. And then our key vector, we are going to see what this all means. For now, let's just go with plotting our diagram. It's just going to be WK XI. And then our value vector is going to be our VI is equal to WV XI for that particular input. So that's what we have here. Earlier, we defined the second input, this one here, as the query when we computed that simplified attention weights. When we wanted to do the context vector 2, we then generalized it to all context vectors, and then we had our Z1 to Zn doing matrix multiplication. So here we are going to start by just computing only one context for only one context vector. What we're trying to do is, because our query is x2, what we're trying to do is calculate our z2, which is the context vector for 2. If we understand how to calculate the context vector for x2, we were able to generalize it to all context vectors. So we can generalize to calculate all context vectors. And that's what we're trying to do here. And what we do, we get all our inputs. We get all our inputs. And then once we get all our inputs, we then multiply them by these weight matrices. We can jump a bit to code to see where we start setting this up. So let's see when we set it up. Because these matrices are going to be trainable, there's something that is important there. So these are our inputs. Our inputs, remember, this is x1. This is your journey begins with one. This is step, begins with one step. We are happy with that. We have 6 tokens, each with 3 dimensions, as we can see. So let's get our x2, because that is our second input element that we are focusing on. We are going to have our shape of that x, the dimension of the x2, which is our dimension in. Those are the dimensions that we are going to use to create our weight matrices. And here we're just saying the output dimension is going to be a 2. As you saw in our, I'm switching back to smooth draw. So now our output dimension, so our input dimension, these WQ, our input dimension is going to be 3. So our D in is going to be equal to 3. And then our output, what it outputs after the matrix multiplication, D out, we are outputting 2 dimensions. That's what we're outputting, right? Because it's just going to be 1, 2 dimensions. Let's switch back to code and I'll emphasize something. Even though we did that to say D equal to 2, in GPT-like models, the input and output dimensions are usually the same. So yeah, it's usually D2, but we're just doing this to illustrate so that we see something different. But you can play around and see and actually make the D out to be the same as the D in, and that's what happens in GPT-like models. Um, right. So now we initialize we initialize these randomly. These matrices WK, you might have been confused. What is that WK, WQ, WK, WV? Where are they coming from? Well, how do we calculate them? Because these are trainable. They are going to be trainable weights. We are initializing them randomly. Just give me random numbers. Random numbers that have those, it is going to be a 3 by 2 matrix. 3 by 2 matrix, it's going to be random. Then they are optimized during training. So yeah, that's what we're doing. Even though we are putting requires grad equal to false, we just want to keep it very simple. But when you're building these models, as you see later, we actually change this require grad equal to true, which means now when the model is being optimized, PyTorch will know that these need to be optimized as well. These parameters that we have created. But for now, for illustration, we're just putting required grad equal to false. So now that we have, it has initialized random numbers into the matrices again, because we're going to optimize them. These are the random numbers that it created. We used the seed just for it to be reproducible, right? So that's why we use the seed. If you use a different seed, you get different initializations here. So this is our query vector that has been initialized. This one here, WQ, these are WK, these are WV. Again, randomly initialized, right? And now we can calculate our query 2. As we said, query 2 is just going to be WQ multiplied by the x2. So here we're just doing matrix multiplication. And we are calculating query 2, not query 1, because what we are calculating there is with respect to the second input element. So the query 2 is query 2. We do not get, if we're calculating with query 1, here it will be x1 times the query vector, times the query matrix, and then we'll get query 1. But for now, we are focusing on query on the second input. That's why we're only calculating query two. And that's it, simple like that. Then we calculate the key two. Key two is just going to be x2 matrix multiplied by that w key. Then the value two that we calculate, same thing. So these are now the result. And if you compare them with what we had in smooth draw, those are, as you can see, 0.4 and 1.4, 1.4, 0.4 and 1.1, 0.3 or 0.4 and 1.0. And that's, if we go back to our smooth draw, that's exactly what we had. That's exactly what we had here, right? So these are now, this is now the this is now the query vector, and this is the key vector, and the last one is the key, is the value vector. And those are the ones that we just calculated. And these are randomly initialized in the beginning, randomly initialized. We randomly initialize them because they'll be optimized during training. But for now, we just randomly initialized them. Okay. So now that we have those vectors, we so now, yeah, so the output of these calculations is going to be two-dimensional vectors, since we said the number of columns of the corresponding weight vectors d out equal to 2. So we will still require, though, the key and the value vectors for the other inputs that we are not focusing on. That's why we have these. And let's see us calculating them in code. So we switch to Google Colab. So these are going to be the keys. And here what we did, we just used the whole matrix. Matrix, this was showing how to do it for a particular input. The query will be for a particular input, but there's no need for us to do particular calculations for key one, key value two, key three, key three, value three, key, because they are going to be calculated no matter the one that you're focusing on at that particular time. So we might as well just use matrix multiplication straight. So that's what we just did here. We calculated keys and values for all inputs because they are calculated for all inputs. The query is the one that is calculated for that particular input. So for the keys, that's what we just did. So that's why we have 6 of them with 2 dimensions. So this is the key vector for the first one. You can go back to where we wrote it in smooth draw, and you see that is the output, the key vector for the first output, for the first input, and then key vector for the second input, third input, fourth, fifth, and then this is the key vector for the last input for that step. So now that we have those keys, we also have the values. This is the value vector for the first input, value vector for the second input, value vector for the third input, value vector for the fourth, fifth, and then this is the value vector for step. Compare it with what we wrote when we were writing manually. You see this aligns. Now that we have those, right? From these outputs, what we have successfully done is we've projected the 6 input tokens from 3 dimensions down now to a 2-dimensional embedding space. As you recall, let's show what I mean there. As you recall here, we started from 3 dimensions, but then now we are dealing in 2 dimensions at this stage. That's where we are now. Now that we are there, that's the first step, right? First step is calculating these query key vectors, right? Query key value vectors. That's what we're calculating. Now that we are at that stage, what do we do next? We actually just do attention scores. Now we are now calculating attention scores. And this is where the query now comes in. We now take, in this example, we are at stage number 2, right? We are at input number 2. We now take the input, the query vector for that input. We take the query vector for that input, and then we use it to then calculate attention scores. So using that query, what we're going to do is we're going to take that particular query and the key vector. It'll be as if we are doing some lookup here in like a table. 0.7. So what we're doing now is we are saying take that query vector for that particular input that you're dealing with at that particular time, and then multiply all the keys that you calculate for all for all inputs, including itself, for all inputs, for you to calculate attention scores. So it's going to be or vector multiplication, yeah, matrix multiplication. So our 0.4 and 1.5 multiplied by our 0.3 to get the first attention score. So our first attention score for input number 1 is going to be 1.2. That is our attention score. And this is now what we had previously. It is our W21. So it is the second input with respect to the first one. So that is our W21. To calculate W22, we take that query vector, and then we multiply the key vector for input number 2. So it's just going to be our 0.4, 1.4, and then we have our 0.4, 1.1. If you want, you can use dot product. 0.4 times 0.4 plus 1.4 times 1.1, and then you get your 1.8. And this becomes our W22. That's what we have now, W22. So this is the attention score here. And all the way up to the last one. You take the query vector again for that particular input that you're doing, and the key vector now for that, for the so here I'm saying you take the query vector for what context vector are you calculating? You're calculating context vector for vector number 2. Cool. So you take the query for vector number 2, which is Q2. This is what we have, Q2. And then you get the query vector for the last one. This is the key vector for the last one, Kn. And that's what we have here. And what you'll find is this is 1.5. 1.5. And this becomes our WN2. That's our WN2. Right. So now, perfect. We have our attention scores. Now that we have our attention scores, these are unscaled attention scores. As you remember, attention scores are unscaled, and they are computed as a dot product between the query and the key vectors. Since we want to compute the context vector for the second input token, the query is derived from the second input token. If we want to do the context vector for the third token, we'll extract the query for the second token. And then and so on and so on and so on. Now that we have that stage, where we are at that stage, we'll have calculated our attention scores. I'm going to just finish this part, and then we'll go to code, and you'll see it in code. Now you remember that from attention scores, because these are unscaled, we need to scale them. And when we scale them, when they are scaled, when they are scaled, we'll then create what are called attention weights, right? So let's scale them. So scaling here. The scaling we are going to do is slightly different to the scaling that we did previously. Previously, we just applied soft max, but right now we want to compute these attention weights by scaling the attention using a slightly different soft max function. But yeah, let me actually show the code so we don't have too many things to show when we get into code. So let's see what I'm saying here. Okay, now these are computing the attention scores. So you can use the keys. So this is the key 0, right? And then we just said attention score, that is our W21, is just going to be the query 2 dot these keys, the key 1. And this is the attention score for input number 1. Same thing, attention score for input number 2, number 3, number 4, number 5, number 6. Number 6, you just get its key key value from our keys matrix. Then you calculate our W26 using the query 2 and the key 6. And that's it. So that's what we have here. Since we have 6 inputs, we have 6 attention scores. That makes sense. Here we are now just doing it in one step instead of doing it. Here it was for illustration purposes when you're calculating one by one, but here we just do it in one step as matrix multiplication. So these are the attention scores now. And those are the ones that we want to normalize. Because when we want to compute the attention weights, we have to normalize them. But the difference is where we now scale the attention scores by dividing them by the square root of the embedding function. So we're not just going to do softmax softmax just like that. We're going to actually say softmax attention scores divided by the square root of the dimension. And DK, yeah, we're just using DK, but it could be DV or anything because we initialized our weight matrices with the same output dimension. So DK will work. We can use DK, DV, whatever it's going to be. It's just as you remember when we initialized our weight matrices here, we embedded them into size 2. We embedded them into size 2. But what we could have done for for s- so you see here we're saying key shape is equal to 2. But for GPT models, they use the same as the input dimension. So there won't be much difference what dimension you use there. But for illustration purposes, that's what we're just doing here. So DK is equal to 2 in our case because our keys, the shape of our keys is 1, 2. So we are taking the second element, which is just 2, and that's what we are using. So here it's just going to be square root of 2. That's the difference that we are going to put there. So we normalize by this embedding size because it improves in our training performance by avoiding small gradients. When scaling the embedding dimension, which is typically greater than 1000, these large language models, sometimes you're doing these dot products that we are doing here, that we're doing or that we did here, will, will result in large dot products that can result in very small gradients. And when we're doing propagation, then it will be difficult. Those gradients will suffer something called the vanishing gradient problem, and we'll see later. Later, we'll actually, when we're talking about softmax in one of the when we're doing fine tuning around that chapter, you're going to see the problem with vanishing gradients. We'll actually do like an exercise where you see where you see those. Because the softmax function behaves more like a step function when we have those very small gradients. And when it comes to backpropagating through a step function, it becomes difficult to do that. So these small gradients, they can drastically slow down learning. And then because they are very, very small, our optimization becomes very, very slow. So which means our training, it can actually stagnate. Our training can stagnate because it's not updating quick enough because of this small gradient. We update neural networks based on the gradients. So if the gradients are very, very tiny and they're changing very, very small, imagine if our gradients are now resulting in things like 0.000000002, and then it becomes 0.000000017. Our updates are very, very, very tiny. And because they are tiny, our training would then stagnate. So we are hoping that as the dimension blows up, because our embedding sometimes, you know that the embedding for GPT-3 was like 12,000. If you do dot product in 12,000 dimensions, it will result in very large dot products, which will affect our softmax function. So now we are just trying to, with this square root is just trying to reduce that impact of those of the large embeddings and embedding dimension. So this part here is actually very important. This is why when we are doing, if sometimes when you read up or read up and then you hear about something called a scaled dot product attention, it is actually this. This is why it's called scaled dot product, because we would have scaled it. Would have scaled it, and in our case, it is scaled by square root of the embedding dimension. In other architectures, people have played around with different ways of scaling, and you can play around. Why are we doing square root? Play around, remove the square root, maybe do a cube root or whatever it is, and see how it affects your training. Square root was just safer for the GPT models. Now that we have calculated, I thought that was very important to emphasize. Um, so now we have our attention weights. We've calculated our attention weights using that scaled softmax. So now we are switching back to we're switching back to our smooth draw, so we can explain this part here. So let's switch back. Okay, let me just switch back. Yeah, now that that is we've done our scaling. When we apply that that particular scaling, which is our softmax, uh, we apply our softmax on our attention scores, which are divided by the square root of the embedding dimension. So this is EMB, square root of D dimension of the embedding. Like that, what we'll end up with is something like, let me get my numbers correct. So now we'll have with this, when this is scaled, it becomes 0.1. And then this, when it's scaled, becomes 0.2. And then the last one, when it's scaled, all of the ones are going to be scaled. All these attention scores are going to be scaled. Even the ones that we haven't written down here, they are going to be scaled. And what we have now are our attention weights. We now have our attention weights as step number 3, right? Just like previous, just like previously when you didn't have trainable weights, we now have our attention weights. And like previously, when we have our attention weights, what is the next step? The next step is now just to calculate the context vector. So this becomes our alpha. This becomes our alpha 2, 1, alpha 2, 2, all the way up to alpha 2n. Brilliant. Now that we have those, we are now going to put all of them together to calculate the context vector for input number 2, the one that we're doing now, one we're dealing with. We now put everything together. You remember that in our previous video, we then had to put everything together, or like I think it was the one before the previous video, because the previous video was putting everything together into just one function. Here we are focusing on the second one. So with the second one, let's now compute our context vector. So to compute our context vector, we we are going to use these attention weights just like we did, because they serve as a weighting factor that weighs the respective importance of each value vector. That's the difference. Previously, we're calculating our attention weights were being applied on the actual inputs themselves, but then now we are applying the attention weights on the value vectors. So now that we have our attention weights, let's grab our attention vectors. Let's go up. You remember we split our inputs into keys and values. So this is where the values are now coming in. We now grab our value vectors, and those are the ones that we then put attention to. So this will be attention to um 0 0.1, 0 0.8, and then we have our value vector for input number 2, which is 0 0.1, 0 0.4, 0 0.1, and then the value vector for the last input was 0 0.3 and 0 0.7 and 0 0.7. So as before, we can use matrix multiplication to obtain um the outputs in one step. So we'll show that in our code. But I think maybe let's just go to code and then we'll come back and then we'll see here. Cool. So in our code here, we have calculated our attention weights. So our attention weights are going to be those attention weights with the value vectors. So each one of them, it will say the attention weight for number 1 and the value vector matrix multiplied by the vector for number 2 plus that plus that plus that. So that's what we are doing here. So we are saying for the context vector number 2 is going to be the attention weight matrix multiplied by the values matrix, because we did values matrix in one step. We could have done this manually. Let's see if we're doing it manually without doing matrix multiplication in all of them. What we would have done here is to say 0 0.1 0.1 multiplied into this plus what is our attention is 0.2 into this plus 0.1, which is our which is our attention weight for the last one, into this plus. So we add all of them. So these attention weights are now being applied on the vectors, on the vector matrices like this. And we add as we calculate 0.1 times this and 0.1 times that. So it's going to be maybe 0.01 and then 0.08 plus. The same thing happens here. Plus, and all of that. I think it's 0.01. I may be mistaken, but yeah, I think it's 0.01. But I think you get the idea. Now, when we add these, this is going to add the result for this, and then the second dimension is going to add the result of this, and we'll have our context vector. And then our context vector in this case is going to be 0.3 times 0.8. That's what we're going to have. Let me just confirm something here. Yeah, it's going to be, I was just confirming if my matrix calculation was correct there. I think it was correct. So it's going to be 0.3 times 0.8. And this becomes now, this is the context vector 2. Context vector 2, which is equal to our Z2. That's our Z2. Previously, again, emphasis. Previously, we applied the attention weights to the actual inputs themselves. That were 3 dimensions, if you remember. But then in this case, we are applying the attention weights onto the value vectors for each input, because we split the inputs using these using these matrices that we initialized. And then so now we had our value, we had our V1, our value 1, and then this became our K1 or our Q1. And this became our K2, this was our Q2, K2, V2, all the way up to Kn, Vn. So this K gets used to calculate the attention scores. It gets used to calculate the attention scores when we apply the respective query vector. So the respective query vector times that key of that input gives us attention scores. And when we get the attention scores, we then scale them using the softmax with the square root of the dimension of the embeddings. And then after that, we now have our attention weights. Attention weights, then we grab our value vectors, and then we apply them, and we calculate our Z at that particular input. So that is our Z2. That's how we calculate our Z2. Here in code, when you get into code, we just did all of that in one step. So the attention weights and the values, and then we calculated our context vector 2. As you can see, 0.3, 0.8. As you can see in the next video, we're going to just now consolidate everything, because here we are focusing on input, second input. Now let's consolidate when we want to do for all inputs, so that we calculate all attention, all queries, all keys, all vector, all values into matrices that would then give us our attention scores matrix. That score matrix would then be scaled, and we'll get our attention, our context vectors. Instead of just focusing on the second context vector, we now have all the context vectors. So we'll see that in the next video.